My name is Anselme. I'm working with a team of researchers from Nancy in France. I'm going to present our work on how to generate proofs of eligibility using the OpenID standard in the context of e-voting. First, I will present e-voting in general and what eligibility is, and then I'm going to present our new protocol. So similarly to traditional paper ballot voting systems, e-voting systems should ensure some properties. First of all, the votes should remain private, meaning that nobody else than the voter should learn who they voted for. And the integrity of the result should be protected, so nobody should be able to manipulate the result of the election. These two properties should be ensured even in the case of a malicious voting server. So for example, if the organizer of an election is corrupted, it should not be able to manipulate the result of the election or learn who voted what. This is done in many e-voting systems by letting the voter encrypt their ballots and publishing those ballots on a public append-only database called the bulletin board. This is a simplified overview, but it's enough for our purpose. I also want to point out that e-voting systems are not only an academic research topic, but also used in the real world by organizations and also governments. So to talk about eligibility, I'm going to present an attack that many voting systems suffer from. As I said, in our threat model, the voting server is malicious. So what it can do is forge a ballot and just send this ballot to the ballot box. Somebody looking at the ballot box will not be able to distinguish it from a legitimate ballot. We miss some kind of evidence in the ballot box that allows us to differentiate a real ballot from a fake one. As I said, many actual e-voting systems just ignore this issue and trust the voting server not to do this. The systems that attempt to fix it sign the ballots, meaning that they're going to let the voter, using his signing key, sign the ballots, and the signature is going to be forwarded to the ballot box, allowing an auditor to verify the signature and check that it comes from a voter with a legitimate signing key. For example, this is done in Estonia, in the Estonian voting system, where each citizen has an electronic ID card that allows them to do exactly this. But in many situations, there is no such public infrastructure that allows each voter to have a signing key. So most of the time, in voting systems that sign the ballots, there's the need to set up an extra entity that generates those keys and sends them to the voter. This comes at a significant cost and also requires this extra channel. Another issue of signing the ballots is that the signing scheme used might be broken in the future, meaning that the signature which are published on the ballot box might leak some private information. So currently there is no solution that fixes ballot stuffing and both preserve the privacy of the voters and is practical enough. We first looked into the practicality issue of it, aspect of it, and searched for existing infrastructure that could provide this signature that we need. So we looked at the OpenID standard. OpenID Connect is a protocol that allows to delegate the authentication to a third party. It's widely deployed, so many big tech companies, but also governments, provide such a service. Here is an overview of the protocol. So when you go on a website and want to use this sign-in with, for example, Google button, the website, called the relying party in the spec, is going to send a challenge to the ID provider. And it's then you as a user are going to have to log in and give the permission to share some information, often the email address. And then the ID provider is going to send back an ID token that contains this ID, and the whole token is signed by the ID provider. If we just try to use OpenID in the context of e-voting, we realize that it's not very helpful because it's just authentication, non-transitive. So the voting server, which is malicious, can just pretend that it happened well and cast a forged ballot anyway. You might notice in my diagram, I left an implementation detail, sorry. So this nonce n in OpenID has the purpose to make sure that the token is freshly generated for the session, because the nonce is going to be included in the ID token. So our idea was to link this nonce to the ballot of the voter meaning that the signature returned by the ID provider is going to be linked to the ballot too, and to use this signature as evidence that we publish on the ballot box. So now before we actually design a protocol with this, there are some key points we have to pay attention to. First of all, the voter should have the last words on when this the ballot is validated and signed. Otherwise, the voting server can reorder ballots or play some other tricks. Second, the voter should make sure that it's their ballot that is signed and not another one. And last, the data that is published on the ballot box should not reveal anything about the voter. To fix those points, we designed a protocol that we call ZOIDELI, which stands for OpenID for Eligibility. And it's an extension of an existing and generic voting protocol. The only assumption we make is that the voter at some point sends a ballot to the voting server, and later this ballot is going to be forwarded to the ballot box. In between, we add an OpenID Connect authentication flow and use the token and the signature as evidence on the ballot box. To solve the issues I mentioned before, we're going to add some messages around the OpenID flow and tweak a bit the OpenID flow. Yeah. So first, to give back control to the voter on when a ballot is validated, we're going to let the voter commit to the ballot before the OpenID flow and use the commitment value in prime as nonce for the OpenID flow. Then we're going to let the voter reveal this commitment only once it checked that the token indeed is valid for its ballot and ID. Second, we're going to let the voter inspect the oath request on its way from the voting server to the OpenID provider to make sure that the nonce and prime is indeed valid for its ballot. So with this, we got a protocol that adds proof of eligibility. We wrote some proofs. I'm not going to bore you with the details here. There's one thing left, though. We publish the ID token in clear on the ballot box, and the ID token contains the ID. So we just tell to everybody who voted and who didn't. To fix this, finally, we use zk-SNARK. We replace the token with a proof of a valid signature. If we look at the content of the ballot box, after a ballot has been cast, we're going to remove the token and instead replace it with a zero-knowledge proof that the prover, in our case the voting server, knows an ID such that the signature is valid. And this statement is polynomial, so in theory, it's feasible to make a zero-knowledge proof out of it. But in practice, it contains a hash function that is SHA-256 in our case. This is a constraint from the OpenID specification, so we cannot replace it with some ZK-friendly hash like Poseidon. And moreover, there are many of those hash functions in this statement, so the proving time is very high with a naive implementation and not usable. To fix this, we used a SNARK framework and optimized the circuit to only have one SHA-256 preimage in the circuit. We used the Plonky2 framework, but made sure that the design of the circuit is generic to be able to use another framework. We also ran some benchmarks that showed that the protocol is useful in large-scale elections with millions of voters. This is thanks to the fact that the proofs are generated on the voting server. So to scale it up, you just need to have a voting server with more resources, and they're very parallelizable. So it's easier to scale up. All right, so I was fast. To wrap up, we designed a new protocol that extends an existing voting system to add verifiable proofs of eligibility using OpenID. We designed the SNARK circuit that protects the privacy of the voter in our protocol. We also implemented a proof of concept on top of the Belenios voting system. It's available as in the artifact. And we wrote some machine checkable proofs of security using the POVAVE tool. That was it. Thank you for your attention.